Lesson 11.2 is about the areas of parallelograms, triangles, and rhombuses. Okay, first of all is a parallelogram. Any parallelogram has the formula area equals base times height, just like a rectangle, because a parallelogram is just a rectangle that's been pushed to the side. So anyway, base times height. Notice, very importantly, that the height is measured with a perpendicular segment to the base that goes, it's an altitude. And so the base times height of a parallelogram represents the area. Next is the area of a triangle. Every triangle has the formula area equals 1/2 base times height. So multiply together, get the product of the base times the height and divide it by 2, and that's the area of a triangle. Not surprising, because this, we fill in the missing part of what you see is really just half of a parallelogram. It's not surprising that the triangle is half the area of the parallelogram. So again, 1/2 base times height. Notice that the height is still an altitude of the triangle, drawn from, if I put the base horizontal to my eye, I go to the highest point on the triangle and drop an altitude down to measure the height. Okay, and the last one is the area of a rhombus. Remember that a rhombus is a parallelogram with 4 equal sides. The diagonals of a rhombus, remember how they always intersect at a perpendicular to each other, and of course they bisect each other. Well, the area of a rhombus, if we divided the rhombus into 4 little right triangles, could actually be determined using the dimensions of those diagonals. And so as it turns out, if I look in this example, if the purple diagonal, let's call that diagonal 1, and then let's call the green diagonal 2, the area of the rhombus is actually half of the product of those 2 diagonals. And I can show you this, why this works in class. It's going to be beyond the scope of this lesson. But basically, we can find the area of each of these little triangles, right triangles, that are inside of the rhombus, and we would get back to, we would be able to derive that it's equal to 1/2 times the product of the 2 diagonals to get the total area of a rhombus. Okay, so for our first simple example, I have a parallelogram here, and I see that I have a piece drawn in that's looks like this is supposed to be perpendicular to the base. It's a little altitude drawn in, and I notice that if I know that the base of this entire parallelogram is 2 plus 10 or 12, but I don't have the height. So I can find the height by using the fact that I've got a little 30, 60, 90 right triangle here. And the 2, this side that's 2, is across from the 30-degree angle, so that's short leg. So if I multiply that by √3, I can get the height and get long leg, which would be the height of this parallelogram. So the area is going to be the base times height, or the base of 12 times the height of 2√3. So that's going to be 24√3. Okay, in this next example, I also have a parallelogram, and I don't have any altitude sketched into this to get the height, and that's something that you're going to have to realize you're going to want to do a lot. So I see that I have a base here of 9 on this, or the base at the top is 9. And if I drop an altitude down right here from this corner, I've created a little 45, 45, 90 right triangle on the left. And if the hypotenuse of that is 6, then each of the legs, this leg here and this leg here, are 6 divided by root 2, which is 6 divided by 2, or 3, times root 2. So that means that the height is 3 root 2. So the area of this figure is, of course, base times height. So it's a base of 9 times a height of 3 root 2. So the area is 27 times the square root of 2. Okay, this next example is just a simple, it's a triangle where I'm given a base of 46 and a height of 12. So I know that the area of a triangle is 1/2 base times height. So in this case, this is 1/2 a base of 46 times a height of 12. So that is 276 square units. Okay, in the next example, I have a hexagon, and I can carve this up, as I've shown here, into some parts. And then, first of all, in the rectangle in the middle, I know that I've got a base of 10. I don't know the height. I want to find that. So I look over on the left and right where I've got two apparently 90-degree, some right isosceles triangles. So that means that these are actually 45, 45, 90s. Okay, this is a 45-degree angle, and this is a 45-degree angle. So anyway, if the legs of those are 8, it means that this hypotenuse of that is 8 root 2. And that's, of course, on both sides of this. So I know if I first of all just take the area of the rectangle in the middle, that is base times height, or 10 times 8 root 2, or 80 root 2. Then I want the area of the two little right triangles, and that's going to be 2 times the area of one of them, and the area of one of them would be 1/2 base times height. So the base of 8 root 2, oh, I'm sorry, okay, a base of 8 and a height of 8, because if I took this around and spun it and looked at it like so, any right triangle, the base and height can be measured like this. So I've got the base of 8 and the height of 8. So that's 8 times 8, or 64. So it's the combination of those two pieces, the two triangles plus the one rectangle in the middle. So I can write that as 64 plus 80 root 2, because those are not like terms. And if I need to get a decimal approximation of that total area, I could. And that's it for the areas of parallelograms, triangles, and rhombuses.